Okay, so up to this we have done. In case of purchasing perspective, then we can go for the least cost is the main parameter, and in case of you go for that means design perspective, that will be another key problem. Rajata, I can't use the present mode without this.
Okay, yes, sir. You can't draw over it, so that's the thing.
It is a big problem because
So
I can't. Yes, yes.
so then you can save it as a PDF and then open it in Acrobat Reader and then go to the full screen mode. It will be better, I think.
But Acrobat Reader,
But
I can't
export as
edit it.
PDF.
I can edit external. External software is not installed in this actually my home system. That is the big problem. Okay, I will now do interactive mode today. Today just I am showing the design. Tomorrow I will do the manual problem in my lab. Okay, so in the perspectives purpose, this is the point you just remembered that we'll go for the least cost approach. Okay, and second is that through here I will do all the pointing, and then best least cost. Second purpose is that in design perspectives best performance improvement, you remember that here also best performance, here also best performance improvement, and also least cost and best cost per performance, cost per performance. You see this parameter and this parameter almost same. The one parameter we have just come to know that performance improvement is there in the scope of or not. Second, you will find that the basis for comparison, the metric for evaluation. So these are the both required. So now let's see one example, which is faster. One is Ferrari, 170 mile per hour, suppose with two people only, and school bus 57 mile per hour, and that is 40 people. Who is faster?
School bus.
Ferrari.
School bus.
So
No,
Ferrari.
I mean, sir, Ferrari, sir, Ferrari.
Ferrari. Okay. Now, which if I consider the raw speed, be careful. Here, I have not considered is a single channel. I have considered a multi-channel. So both can run parallel. If suppose, so if we consider raw speed, then you will find that Ferrari wins. Am I correct?
Yes,
Nahi.
sir.
Okay.
Yes, sir.
Now, if you consider particularly suppose in case of throughput, next part is the throughput, and particular duration, you will find that Ferrari will take 340 passengers, but within the due time, school bus will take 2280 passengers. Now, which have the maximum throughput?
School bus.
Now, then you can come to know one point that just for your knowledge, I am asking, just fast, you will purchase your computer based on the fast, or you will purchase your computer based on the throughput. Now
Sir,
that is
depending.
the criteria differs. Am I correct or no? Now criteria completely differs.
Yes, sir.
Yes, sir.
See, in these cases, range, reliability, school bus, whatever may be. So the performance comparison will be according to the our desired goal. Both the performance may not be at per criteria. If you are considering only speed, maybe some application where large data large data handling is not required, only for fraction of data is required, but the speed is main thing. That time I think faster processor will be the best thing. But if you go for the that means this issue, that means in earlier slide I already shown that if you go for that purpose, that means cost, our main cost per performance, that is the very in the best cost per performance. If you measure that time, there is a issue will be the throughput. So what ways can be used to determine performance of a desktop PC, or what ways can be used to determine performance server? Both will be same metric can be applied here. I think not. As a server throughput or instant replica, that means reply or the execution of the instruction is a very important point. But in case of desktop, only the task which is assigned to him, execution successfully is the main criteria. Then automatically you will find two more things. How long does it take to run my favorite program? That means CPU time. Again, you will find response time. Again, you will find batch throughput. My question, CPU time and response time. Okay, is this same?
No, sir.
No, sir.
No, sir.
Let's see. Can you explain anyone from your side why it is not same?
Sir, response time depends on cache memory mostly.
Not tighter cache memory. Just apply common sense. Don't apply anything hard and fast concept like mm, cache memory or something else. Just tell me what is
Sir,
CPU time and response time.
CPU time is the processing time and response time is the which in how many in how which in sir the time required to respond
Time required.
to respond to get the response from the output devices.
Oh, but not I am asking. Mhm. That I am not asking. Not clear to me. Any other point? Let's see. I am telling that to compare to computers, we can compare the execution time. Okay, we can execution time of the same program on two computer. That should be your criteria. Same program on same computer. When you run the program, suppose you are making a sorting of 1000 elements, and one student applying bubble sort, another student applying quick sort, maybe. And if you run on the same computer, maybe the element will be 1 lakh or 2 lakh, you can increase, no problem. You will find there is a little bit difference, that bubble sort little bit slower than quick sort. It will happen, we know, because already you compared, but in the same computer, same machine, so lower execution time is always better, that we know. But normally interest in reducing response time. Response time is that the time between the start and the completion of the task. Why I am telling the response time is another very important point, you will gradually understand, because response time critically is a fully depend on the part of, that means suppose it is your CPU, it is a CPU, you have submitted request, and until or unless you are not getting the final output, you will wait. So the time between the submission of the time between the submission uh, and sorry, you can say start of the completion and the completion of the task, we can say the time between the start. Okay, that means start and finishing. What is doing today's computer? Oof. Writing something, adding something. Okay, so response of the, I am telling the time between the start and the completion of the task. So this is the 2 points. Suppose in CPU a process is submitted and you are getting the finishing, so it may be x and with the y time. So I can say y minus x the x time. But in the y minus x time, it may happen that the CPU is not utilized by the item, suppose processor P1. Processor P1 is not only handling the tasks. Processor P1 not only handling the tasks. Just remember that. Other processor maybe that time was there, P1 in wait state, and after certain time P1 again feedback to the process. So like in this way, we can say that in terms of particularly this part, performance way, I can say performance for any matrix will be 1 by execution time. Remember, performance and execution time is just inversely proportional. So that's why if you increase 2 gigahertz, 3 gigahertz, 4 gigahertz, 5 gigahertz time, suppose the clock speed, so automatically the performance will boost it. The performance will increase. That what we understood. So to maximize the performance, need to minimize the execution time. If you minimize the execution time, so automatically performance will boosted. So that's why if x is n time faster than y, we can write performance x by performance y in reverse way, execution time y by execution time x equal to n. So this is the factor you can write like in this way. Is it clear? Throughput is that the total amount of work Okay, total amount of work done in a given time important to data manager. Okay, decreasing response time always improves the throughput. That means large number of output will comes out. Suppose we want to distinguish elapsed time and the time spent on your our task. CPU execution time is CPU time the CPU
Sir,
spends working
sir,
on a time.
sir,
Time, yes.
sir, could you repeat what throughput is, sir? I didn't get the definition, sir.
Which one?
Sir, throughput, sir, throughput.
Throughput is the number of process comes out successfully or the number of process executed successfully per unit time or per time you have specified. Then
Okay, sir.
the number of process successfully executed, that is the throughput.
Okay, sir. Thank you, sir.
If the response time becomes very slow or sorry low, then automatically large number of process will be executed. Then throughput automatically increases. So CPU execution time, always the time the CPU spend working on a task. Remember why I am mentioning the time CPU spends on the process and the response time of the process always may not be same, because the CPU time does not include the time waiting for IO. IO means suppose your process requires some file handling or file read and write output or requires some process other process execution. So that time CPU send your process to the waiting queue, take the data and again come CPU may handle other process. So that's why the time waiting for IO and running other programs not considered in the CPU time. So CPU time always just you find that CPU is utilized for doing the tasks. So that's why response time will include CPU time plus IO waiting time plus other programs response. So including all this, response time is calculated. So response time will be always high. But even if we can minimize this, the response time, then it will be beneficial for us. That's the I want to mention. Second is that CPU execution time for a program. CPU execution time or a program is the clock time or that purpose. So CPU execution time, that number of CPU clock cycles for a program, suppose X, and the clock cycle time maybe 2 gigahertz or something. So clock cycle time is the inverse of the frequency. That's why I've written inverse of 1 by f. So automatically you'll write the CPU execution time for a particular program is the number of clock cycle divided by its clock rate. That means 2 gigahertz something, whatever may be. So cycle time, it may be picosecond, nanosecond. But if you write in the frequency, it should be inverse of the frequency. So it can improve the performance reducing either length of the clock cycle. That means we can reduce the number of clock cycle required for the execution of the process. We can reduce this or the number of clock cycle required for a program. So that's our target, the clock cycle, how we can reduce. So again, execution time, since the cycle time of the computer is constant, we can express time in terms of CPU cycles. So time, computer CPU cycles, but cycle time. And cycle time instead of inverse of frequency, that's why I'm writing cycles divided by clock frequency. Is this part clear? What I mentioned here, is this part clear?
Yes.
Because cycle time, that means this part is 1 by f. And f is our frequency, clock frequency, that is coming in the market 2 gigahertz, 3 gigahertz, like in this it is coming. Okay, so
Sir,
this part actually, yes.
What is sir? What is why it is called clock cycle, sir? Clock. Why it is called clock, sir?
Number of cycle.
Yes, sir. Clock cycle. I mean,
Cycle. Why I mentioned that? Because the cycle time is constant. Already in the previous slide I have mentioned that to tell our what is our target, that CPU clock cycles for a program. That means to execute an instruction, how many clock cycle required, that I will given in the exam. Generally, to find out the clock cycle, you have to use the program of timer in the C program and stop the timer when finish is coming. The difference between the total, you will get the total clock cycles. If the timer is coming, you can say in case of timer is coming the second or picoseconds, the total time is required. But the number of clock cycles required, you can also estimate based on the total clock time and you can say the architecture part. I think it will mention that clock cycle for if the program is this clock cycles is required for a particular program. That I will mention explicitly in the exam. Okay, the particularly length of the clock cycles and the number of clock cycles I will mention. Is it clear? To find out in the
Yes.
gradually, it is a hardware factor. From the hardware, you can find out the length of the clock cycle, but how many clock cycle recur based on the time you can compute. Am I correct? Are you getting my point or
Yes.
not?
Yes, sir. Thank you, sir.
As you told that the performance can be improved by the decreasing the cycle time. So that is a big issue, decreasing the cycle time. So hardware solution, use faster technology. So automatically that's the main problem. I'm telling the architecture issue. That means use some Pentium i7, i10, i9, whatever technology, faster technology. So cycle time will decrease. But the number of cycle of the program, it is completely software and hardware both. That means write a better program to reduce the number of clock cycle. Here for timing, you consider the number of clock cycle just equivalent to number of time. If a clock cycle equal to 1 unit of time, so your program require 10 unit of time, I will consider 10 slides for the sake of our understanding. Okay. So that will I consider the time and divide by with the frequency, automatically will get the our required the clock cycle required for this one. So software purpose write better program and hardware purpose because hardware is always fixed. So you need more. If you would like to clock cycle reduce, then redesign the CPU. This is the operating system part. That why I told you sometimes whenever a process is ready or sorry program is ready, then it goes to the process. So process is nothing but program in execution. You will find when program entered in this zone, program is called process. Okay. During the computing, sometimes it happen that process requires some another data from other process of some memory. So it will waiting state. The process will be goes to the waiting state, and CPU will this is the CPU. CPU will take other process to execute. And when it will get data will be available, then again it will knock the CPU that the process data IO completion event is signed. Then CPU will again handle this. Some interrupts may be happen from CPU side. So all these things CPU time is not considered. It will be considered response time. Response time is up to this from submission to finishing. This is our response time. But inside all these things, the interrupt, waiting, short time scheduling, this is not considered in our CPU exist. CPU only ready and running. Ready and running. In between this, CPU time is computed. Okay. So it is the OS related issue. OS can do fast come fast serve. That means fast process will be submitted until it is not finished. Whether it is some interrupt or some waiting, you have to finish then come out. So automatically throughput will be decreases. So that's why we are using shortest job first in or maybe in round robin scheduling. Today in this semester you have operating system? No, I think no.
No,
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 sir.
sir.
No,
No.
No, sir.
no, sir.
I
In
think
this
next
semester
year,
we have.
next semester you will find out operating system. That time this will be discussed a lot of issue. That means how process is scheduled. Okay, for timing you just remember that what is the response and what is the CPU time. Now suppose this is the clock frequency. So clock cycle I am telling that the clock rate is inverse of the clock cycle time. So clock cycle time automatically you write the your clock rate inverse, you will get the clock cycle for a particular hardware. So we have written the clock cycle issues and the time 2 nanosecond, 1 nanosecond, 500 picosecond, and what is the clock rate that time. Since you people mostly now, I think we are belongs to this zone. Still, 3.2 is a good computer, about 2 gigahertz. Now, 500 second clock cycle or 200 pico clock cycle, you are just now we are using this type of parameter. This still not available in the market. So this is the clock rate. Now execution time will be the every instruction takes a time to execute. So we have just given some data here. Some instruction may take more or less time than others. The time for instruction is expressed in terms of clock cycle. So suppose add require 1 clock cycle, multiple require 4 clock cycle, compare require 1 clock cycle, and subtraction require 2 clock cycle. This is the clock cycles I have given. So The time to run a program depends on how many instructions, what type of instruction. Suppose if your program all are add based instruction, so you can say 1 clock cycle, but you have a more multiple, then you require more number of clock cycle. So that's why you can avoid multiple by doing addition also. Sometimes it can be better way to avoid a multiplication, apply addition, because it will reduce the clock cycle. So here 30 adds and 4 multiplication require total 46 clock cycle. Even see only 4 multiple multiple multiplier, or you can say multiple multiplication instruction number only 4 and 30 add, but it's 46 clock cycle. So our main criteria is that average CPI you have to find out. For a particular machine A and particular machine B, you always try to find out the average clock per instruction. The cycle per instruction CPI varies depending on the what instructions are used. Take an average CPI. So cycles, total cycles will be the number of instruction plus average CPI. So number of instruction for a particular program, and average CPI you have to find out. If you multiply, you find the total clock cycle. Now it is clear how to find out the cycles. Okay, so the question is come how to calculate the cycle. So cycle you can find out for this one. Now average CPI should reflect the instruction in the program. Okay, so a large program of 4 cycle multiplication should raise the clock per instruction, cycles per instruction more, and large portion of 1 cycle error should lower it. That's I told you. Even large number of error cycle, but your CPI will be less. But a 4 cycle multiplication can increase. So average should be the weighted average of all these things, the number of instruction are using. So for again weighted, I consider that in my program, number of add operation is 40% and multiplication is 10%, compare is 20%, and subtraction is 30% instructions are there in the total, the mix of instruction. So average CPI will be the number of cycle is the ratio 40% and 4 cycles for 10%. That means the number of clock cycle 4 for multiplication, how many multiplications are there. So just with percentage, you will find that 1.6 the average CPI. Now average CPI you have received. So average CPI multiplied with what? Average CPI multiplied with what?
100%.
Number of instructions.
Number of instruction of your program. That means instruction count, I can say IC. Number of instruction, that means what? Instruction count means what? IC. Am I correct or wrong?
Yes, sir.
IC. IC means number of instruction total. So multiply the average CPI, what you will get? Total clock cycles. Yeah, very good. So cycle you getting. Now you know the cycle. So execution time will be what? Total instruction plus total cycle, and cycle means cycles per instruction into cycle time. Am I correct or wrong?
Yes, sir.
Yes, sir.
So you know that cycles will be the execution time will be the instruction count, and C, because average CPI is we know, so CPI clock per instruction per cycle time. Okay, now reducing any one of these three, either instruction count, number of instruction you reduce, or number of clock pulse CPI you try, cycle per instruction you try to reduce, or you can reduce the cycle time. Mainly the reduction of this is fully depends upon the hardware. Okay, but this is in our hand. So if you can reduce these two also, you can get the more beneficial effect. So reducing any one of these three components reduces the execution time. So instruction count reduced through better code, better compiler, and change in CPU design. Generally we people go for this because existing hardware is costly, so randomly we can't change it. CPI reduced through better code again, better compiler, and change in CPU design. CPI, that means clock per cycle per instruction. And cycle time directly hardware technology change, not it in our hand. So now we are comparing two machine. So all the instruction, we can say one way to think about execution time is that it equals the number of instruction executed multiplied by the average time API that I consider. So number of instruction API. How to find out the API? API from the instruction set, you find out the number of instruction of that particular kind multiplied with the number clock cycle required of that kind. If you multiply that, you will get the finally average clock cycles per instruction. So automatically CPU clock cycle per program you will find out. After that, our target is that CPI. Suppose A, B, C, three instructions classes given. Each of the CPI is 1, 2, 3. Okay. Now I am comparing these two. Overall effective CPI for the instruction count. Computing the overall CPI is done looking at the different types of instruction, the individual cycle count at average. So where I see is the count, the percentage, I know already mentioned the number of the instruction of the classes I executed. So automatically it's just finding the average CPI. The way effective CPI, that means you are finding the average CPI. Okay. So automatically the overall effective CPI varies by instruction mix A measure for the dynamic frequency or the instruction across on the program. Now,
Sir, could you go back
yes,
to the part where we were teaching us clock cycles per instruction, sir? I didn't get that formula, sir.
clock cycle per
Instruction, sir.
clock cycle per instruction is essential, but generally for each of the instruction individually we can find out. That's why we take the help of average CPI. Okay, so if you find out the average CPI, that means for a program, how many add, how many multiplication. Suppose you have a 10 instruction. Okay, among the 10, you find 4 is a add instruction. What is the percentage? 40%.
Yes, sir.
2 is a multiplication and it is 20%. So among total 40, 20 and rest other is how much? 40% is the rest instruction, suppose. So you know the clock cycle for add, suppose 1, and for multiplication is 4.
Yes.
Okay, so what happened that you have to multiply the number of instruction present on the program multiplied by kind of clock cycle, the number of clock cycle required of such kind of instruction. Suppose you are using add. You are using add instruction and add require 1 clock cycle for you executing 1 add cycle, and among them 40% add. So zero point 0.4 multiplied with the 1, you will get the average CPI for add. Sorry, clock CPI for clock cycle for add. Like in this other instruction, find it, sum it, you will get the effective CPI for the program. Got it?
So, okay, sir.
Might not be clear a little bit. With some numerical problem, we'll clear it. Okay, just come to the theory I have to finish. See, because today I am not using the pen, so there's the one problem. Tomorrow I will do the rest of the time. Our basic performance equation is there. CPU time, just remember instruction count, CPI, and the clock cycle. So how to find out the clock cycle, that I have shown. Now clock per instruction also you know. So CPU time, instruction count into CPI by the clock rate. Clock cycle time, you will find the your frequency. So now you will find after that those equations separate 3 key factors. Effective can measure the CPU execution time by running the program, and the clock rate is usually given. Can measure overall instruction count by using profilers. I will go to this point because without ISA explanation it will be clear. Now suppose some for CPU time for algorithm, programming language, compiler, you just see the map. Clock cycle is fully technology dependent. Processor organization will help you to find the effective clock cycles per instruction, and also it is a processor organization also depends on the hardware. ISA instructions architecture is the number of automatically, if you are using number of 6 operation uh, for a particular program, if you use a 6 coding style instruction format, I think number of instruction will be very less, and if you use a RIX, number of instruction will be more. But On the contrary, you will find that the 6 instruction require number of clock cycle more for a particular single instruction, where RISC instruction clock cycle for a particular single instruction require maybe less, because very simple instruction, load store or maybe 2 address format. But in case of 6 computer where 3 address can address simultaneously, so huge time may be spent to fetch the instruction from the memory to the register. So that's why even though 6 the instruction count is very less, but RISC is performing better because having large number of instruction, but the each instruction require less number of clock cycle. So that is the one important point you remember. Like in this way, CPI and clock cycle, instruction set architecture depends upon instruction count, clock cycles for instructions, and also clock cycle. Same compiler. Like in this way, for algorithm also we have done. Let's see this example. ALU have 50% I think find the frequency. That means arithmetic calculation. Load, store, and branch have 20, 10, and 20. These are the frequency. Frequency, I can say the number of instruction present in the program, and their total number of instruction divided by total number divided according to a percentage. You will get the 50% of arithmetic logic unit, arithmetic logical unit based instruction. That means nothing but add, sub, mul, such type of instructions. And they are each of them clock frequency requirement, cycle per instruction required mention, because during the addition subtraction I think only register data is required, so 1 clock cycle is sufficient. But during the loading you may load from memory or from other sources, the number of clock cycles is used. For storing, it will store register to memory 3 clock cycle. For branching, it will just jump within the memory or within the register bank, so 2 clock cycle. Now overall effective 1 into 50, 1 into not 50, 50% is 5 into 20 percentage, 10 into 30 percentage, and like in this way you will find that is coming 2.2. So average effective you have found CPI is 2.2, almost average CPI. So we mention overall effective CPI. How much faster would the machine be a better data cache? Reduce the average load time in 2 clock cycle. Now average load time is now is 5 clock cycle. Now if it is reduced 2 clock cycle, that means instead of 2 we'll consider 5, it will consider 3. So earlier example how much 1.0, now we are considering like in this way. So you'll find that if you reduce the clock cycle, it's coming 1.6. Am I correct or wrong?
Yes.
Because
Yes.
here it was 5 into 20, you are getting 1, like in this 20%. Now when to the 2 clock cycle you reduce, if it is become 2, that will be automatically 0.4. Okay, rest of the part same. So just reducing the clock cycle time for a particular instruction, you are getting better performance here. Okay, so now you'll find that our main criteria of this program now reducing 1.6. Now CPU time new 1.6, the total IC is the number of instructions and the clock cycle both are remain same. So actually you are finding that 2.2 by 1.6 the CPU execution time, it means that 37.5% faster. This one, it become faster, 37.5% faster. So question may come, if this is the suppose it is your question, suppose this is your question, and the question is asked, if I change the load clock cycle from 5 to 2, how much faster will perform this computer? Can you tell me how to find out this one? Just now I have shown. Because for the same program, same number of compiler, just IC and CC is same. We are just difference in the CPI value. So CPI differs. Automatically you will find out that which is faster, this one faster or this one is become faster. Now this one is faster, and that is 37.5% faster. So that's I mentioned here. Notice since IC and CC are all are same. Okay. So like in this way, you can find out by changing the different frequency. You can find out the cycle times, and accordingly you can find the better CPU utilization. Okay. So this is the one example. What if two ALU instruction could be executed at once? Two ALU, that means 50% you are reducing. Okay, so automatically this is the time you find out. Got my point? Just reducing the clock cycle, I am getting that the average of our, you can say overall effective CPI is reduced. Here remains even though it is reduced, but the clock cycle not reduced. Can you explain why? Any from your side?
So could you
Here
repeat
was
the question once?
0.5. So 0.5 to 0.25, it is a 50% reduction. But even though earlier also 0.5, so same it is reduced, but here it is 1.6 and here is the 1.95. Why?
Sir, because the size, sir, it's one, sir, so it doesn't have much of an effect also.
Which one?
Sir, the CPI
Uh,
is low for ALU, right?
yeah, we decrease the CPU size for ALU
Yes, sir, and so it doesn't have much of an effect, sir, in the rest of the operation, sir.
because the clock cycle per instruction is very less.
Yes, sir, yes, sir.
Target those instruction which has more cycle. To execute that instruction require more cycle, we have to reduce it. That's the issue. Okay. Now thank you. For this way you can compare. Now if you see this one, tell me which is faster, which is slower. Can you tell me?
Sir, it will system B will be faster, sir, because
Which
less.
one?
So system B will be faster, sir.
System will be faster.
Yes, sir.
Okay. Check.
5 seconds.
Time for A is 10 second and time B recurs is 5 second. So automatically be faster. Now 10 second to run a program and 20 nanosecond clock, and there is a I think 400 million 400 million instruction. What is the CPI? How to find out?
Sir, it will be like the summation. So the time by, yes, sir. That formula, sir. That formula, sir.
Check it. So you can express such type of small scale example, short example in the examination that you have to compute. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now see another example. This one. Assume it takes 1 clock cycle, multiplication take 4 clock cycle, subtraction require 2 clock cycle. Okay, and the same program of a loop is running. I think it is running 10 lakhs time, 10 lakhs times. Okay. In 10 lakhs time, you are just running the program to different compiler produce the following loops in the same code. The same code, and they are doing like in this way. To different compiler produce the following loops for the same code. For the same code, you remember this thing they are telling. So in first case, what will be CPIA? Can you tell me?
11.
Mm-hmm.
11 CPI.
CPIA for the first section A, then CPIA, cycle per instruction. How many multiplications are there?
2.
2 multiplication.
2.
So automatically 4 plus 4, how much? 8. 1 8. Am I correct or wrong?
Sir.
Yes, sir.
Yes, sir.
4 plus 4, 8
Okay.
plus 1, 9 plus 2, 11. Okay. 11 divided by total number of instruction 1, 2, 3, 4. What is the value?
So 2.
2.75. Huh?
Yes, sir.
Okay.
Yes, sir.
In this case, again 1 plus 1, 2, 2 plus 4,
6.
8, 8 plus 2, 10 plus 2, how much? Am I correct?
6.
4, 4 plus 4, 8 plus 2, 10. This coming 10.
1.67, sir.
10,
10 by 6.
10 by 6. 10 by 6.
10 by
6.
6. How much is coming?
1.67.
1.66.
1.666 something. Na?
1.6.
Just I'm writing 1.6 for the sake of. See, same program. Just use of the instruction which have more number of clock cycle increase the execution time. That means you can say the CPI. Okay. So you wanna find out this one? 2.7 by 1.6667 something. So like in this way, if I compare the if I compare this part, whatever I mentioned, this one. Okay. So now you find that time CPI instruction per period. So 2.75 is given. Okay. And suppose the for CPI the 5 nanoseconds, and how many number of instruction count? How many times it will operate? Suppose this is the instruction number count is total is this one, total instruction count. So they are getting 0.005 seconds for time, and for B it is 0.0050 second, very close. Did you get it?
Yes, sir.
Yes.
Okay.
Yes.
So like in this way you can compare the find out, but how to find out the clock cycles, all these things I have shown you. Remember, it is required for numerical problem. So that again we are summarizing this part, that comparing and summarizing. How do we summarize the performance of the benchmark set with a single number? So arithmetic mean you have to find out, and the execution of the time. So just I will share the slide to you today also. So that is the performance metric. Now you can find out some benchmarks are there, that means spec benchmarks is there, MIPS that already I have told some architecture, million instruction. Here it is not that multi interconnected process architecture I am not showing. It is a million instruction per second. Okay, so floating point calculation per second, millions of floating point calculation per second, and some benchmarks are there. So standardizing, whenever you design a new computer, it will be evaluate all these benchmark. Spec SPC is the suitable benchmark. Program thought to be represent for commonly used program benchmark circuit. Actually correspond to the execution times, response a wide range of program, but are they running your program or not? That is the main mistake, and who picks the benchmark. So this is the thing, just for your knowledge I have given you. That means whenever you created any new processor or new architecture, you have to analyze with the system performance evaluation cooperative, that is spec a set of benchmarks, some programs are there in the spec programming system. You run this, find out the CPU time. Again, your another friend has created another CPU. Again, same thing. If you run the spec benchmarks, automatically some output comes out. Comparing the two outputs, you can choose whether your design or your friend design is better. So, like in this way, we have shown some Pentium Pro, Pentium 2, Celeron, and Pentium 3, and they have different clock speeds and flex benchmark their performance little bit and differs. So that we have shown is the earlier version. So better case design on chip versus off chip, and that's why Pentium 3 performs very well comparing others. Same thing they have shown. That means to define the, always you have to go for the spec architecture. Okay, so this is the your main time. So Amdahl's law is that execution time affected by important two parameter, the amount of important and unaffected execution time. So practical effect that make the common case faster. So forget about the rare case. This is a given 70% of my execution time is done on integer addition and 6% on floating point addition. Total execution time is hundreds. So now effective time they have calculated. And what is the effective time of floating point addition? Again calculated. If you compare these both, you'll get a million pass instruction always divided with the millions 10 to the minus 6 per second. So automatically you'll get a MIPS also as a standard instruction computing whatever time you will get, you can compare. So this for your reference I will keep today. You just study. So our main criteria is that always you have to find out the execution time in terms of number of instructions, cycle time, and CPI, and you know how to find out the overall CPU time and the cycle time. You know inverse of the frequency, multiply the number of instruction, you will get the execution time for the entire program. So that will be the up to discuss. Okay. This for our today's session. Okay, so I am finishing this today, and Wednesday we'll start a new chapter. Apart from that, you just remember that you should study